This is an example of an IFE gas table problem. So, first thing we have to do is read the question. A 350 milliliter sample of gas at standard pressure, standard pressure we know is 1 atmosphere, has a temperature of 30 degrees Celsius. What temperature would be needed for the same amount of gas in the same container to have a pressure of 1.25 atmospheres? So the first thing that you're going to want to do is fill in the IFE table. The IFE table gives us a space to fill in the initial and the final values for any of the changing 4 variables that we can use to describe a gas. So the first one is volume. It says 350 milliliter sample gas to start with. So we're going to write in 350 ml in for volume. Then it told us standard pressure. Standard pressure, we said, was 1 atmosphere. And it has a temperature of 30 degrees Celsius. Now, we need to make sure that we always use Kelvin temperature to describe temperature when we are using a math type problem for gas laws. So we need to take 30 degrees Celsius and add 273. The Kelvin temperature is 303 Kelvin. And 303 Kelvin for our temperature. What temperature would be needed for the same amount of gas? So we know we're solving for a new temperature, final temperature. If we have the same amount of gas, that's going to tell us that there's going to be no effect or no change in the number of particles that we have. They also never told us how many particles we started with, so we can kind of put a dash through all of those. Then it tells us that it's in the same container. If it's the same container, then the container volume should be the same. We'll also put a dash through the effect. There's going to be no change in that volume. So the only 2 things that are changing are temperature and pressure. It says that the same container is going to have a pressure of 1.25 atmospheres. What we're going to want to do is indicate what the effect is going to be on our pressure and then on our temperature. We can see that we're increasing our pressure because we're going from 1 atmosphere to 1.25 atmospheres. Then we're going to need to predict what's going to happen to the temperature. Our temperature should also increase. The reason we know that is because of the relationship between temperature and pressure in Kelvin. As the temperature increases, the particles should be moving faster. With more particles moving faster, there should be more collisions and therefore an increased pressure. So both of these variables are increasing together, and we call that a direct relationship. So the next question then is, what is the actual new temperature going to be? So in order to find a new value, our final temperature can be found by taking our initial temperature and multiplying it by some ratio. The ratio that we know, or the numbers that we can use to find a ratio, comes from the change in pressure. So we have 2 options. We can either take 1 atmosphere divided by 1.25 atmospheres, or we can take 1.25 atmospheres and divide it by 1 atmosphere. The question is, which one of those ratios is going to give us a larger temperature than we started with? So what's going to happen is you're going to choose the ratio that has the larger number on top. In this case, 1.25 atmospheres divided by 1. If we wanted a smaller temperature value, we would have chosen the ratio with the smaller number on top. So to find our final temperature, we're going to take our initial temperature, 303 Kelvin, and we're going to multiply it by 1.25 atmospheres divided by 1 atmosphere. When you calculate that all out, we get 379 Kelvin. If you want to report your answer in Celsius, all you have to do is subtract 273 from that. So then the equivalent Celsius temperature is 106 degrees Celsius. And we got that by subtracting 273. But 379 would be our new Kelvin temperature. The last thing we want to do is draw a particle picture. In our particle picture, we know that we want to have two boxes that are the same size to represent equal volumes. And we also want to have the same number of particles in each box. So I'm going to draw 4 particles in each box. And then the next thing that we want to consider is the fact that our temperature and pressure both increased. So to show temperature, we use whooshies. For our initial picture, we're starting at a lower temperature. So I'm going to just draw 1 whooshy and 1 pressure event. So I like to label my pressure events. I have 1 pressure event, and it's clear that you can see I have 1 whooshy. To show an increase in temperature, I'm going to want to draw more whooshies on each particle. So to make things easy, I'm just going to double my whooshies, and I'm going to also want to double my pressure events. So this particle is going to have some pressure events. We've got 2 whooshies, and then I'll draw pressure events on that particle as well. So in this case, we would have pressure events equal to 2. Some people look at that and they see 4 angled arrows or angled whooshies, so they would call that 4 pressure events. As long as you show an increase in pressure, then you're doing good.